Hello, folks. My name is Simon Brightwell. I'm from Senceive, and I'm joined today by my colleague Pete Jones. And over the next 45 minutes or so, Pete and I are intending to give you a little whistle-stop tour through the world of wireless monitoring. I'm going to cover the first part of this presentation. I'll hand over to Pete, who's going to talk about infrastructure applications and deal with questions which we'll cover at the end. So please feel free to drop stuff in the chat, and we'll deal with that a little bit later. We will be happy to share copies of the slides as a PDF. So if you let the organisers know, then we will be doing that. That's available to you for reference. In terms of introduction, I'm going to let Pete do his own, but myself, I'm part of the marketing team at Senceive, and I've been working for a long time, 30 odd years in engineering, doing work in technical and commercial roles in NDT, in geophysics, in geotechnics, and in monitoring. So a range of different project related and nowadays slightly more sort of commercial types of role. So without further ado, let's have a consideration of this big question: what is wireless monitoring, and why is it worth giving up at lunchtime? I think first up, even before that big question, is a bigger one really. Is before we do get involved with a monitoring project, I think it's really important to acknowledge the wisdom of John Dunnicliffe, who is really just asking the fundamental question of is there a specific question to answer? There is no point doing monitoring unless we really understand the reason for that. And I think that's probably quite significant through the course of the presentation today. We're not doing it for the sake of it, we're doing it because there is a reason. We need to understand that reason. And I hope also that the presentation gives you an idea of the places where wireless is a viable, attractive option, and a practical understanding that it's not the answer to every question. It's part of the toolkit. It's a useful tool to have as part of that kit. There are situations, however, for example, really short-term deployments where traditional kind of attended survey and monitoring are likely to be a better, more cost-effective approach. The wireless monitoring solutions that we're covering here are fantastic at a lot of applications where you're concerned about relative movement. They are less suitable for absolute movement, and I think that's quite a significant point. A strength I would point out is the ability to integrate various types of sensor, both movement-related sensing and also geotechnical or structural sensor types into that same network. And we have the ability or the requirement, I think, to combine sensors. For example, if we are looking at an absolute movement requirement, we need to know where our sensors are. So we will need to survey them in through a conventional approach before we start as part of the baselining. And I think for those reasons, this sort of technology is seldom used in isolation. It's generally used as part of a package. So what is wireless monitoring? I suppose a typical setup will comprise three main components. You'll have some sensors. You'll have a communications platform that will allow you to get data from the site to the stakeholder, and you'll need a data portal to allow you to see what's happening. It's no use just getting the data in a black box. You need to see it. So the first part of that little ensemble is the sensors, and the most widely used type of sensor is a tilt sensor. So this is a MEMS-based device that measures rotation to 1,000th of a degree, which in many applications will equate to a sub-millimeter measurement of rotational movement. So it's a precise tool that can be mounted to pretty much anything at any angle. It can be fitted very quickly and simply using a magnet to metal, or using quick fix adhesive to wood or masonry, or it can be drilled and fixed into concrete or masonry, and it can be left there for quite a while. In a typical application, it's not unusual to get 10 to 15 years of life from one of these sensors. And there's a whole bunch of other things. This isn't a complete picture, but just to give you a flavor for some of the other types of sensor that can be included: a crack sensor, a replacement for the old favorite telltale. You don't have to climb a ladder to get the results out of this one. Millivolt sensor allows us to integrate our wireless network with a variety of often third-party sensors, so we can look at pressure sensors and strain gauges, torque sensors, load cells, load pins, moisture meters. A variety of different third-party sensors can be brought into that network. If we need to get eyes on the site quickly before we can get boots on the ground there, then a camera is a very useful way of investigating an alert that our other sensors may have picked up, and allow us to rule out a false alarm, a false alert. These can be solar powered, so they can be part of an intelligent monitoring system at a remote site. The camera can be triggered by movement of some of the other sensors, so it can be a smart way of getting an understanding of what's happening. We can combine the tilt meter with a laser extensometer. So this will allow us to measure the relative movement of two objects: the object that the sensor is mounted to, and something that is looking at, for example, two bridge piers. We'll have a look at some examples of that shortly. And they will talk to a gateway which collates and collects and transmits the data from that suite of sensors to the cloud, and onwards to a data portal where you can interact with it. All of that relies on a communications platform, and there are a couple of important choices here. If you're looking for a dense network of sensors with high frequency reporting, you want to include multiple sensor types, you want to power your gateway from a solar panel, if you want a level of intelligence built into the nodes that can react to events, then the logical choice is what we call a flat mesh system. It operates at a relatively high frequency part of the radio spectrum, 2.4 gigahertz. It's a highly responsive way of connecting a large variety of sensors in a dense network in a short place for high-speed reporting. It does come with some limitations. We can only include up to 100 nodes per gateway, and we have a limitation on distance of up to about 300 meters in best conditions between the gateway and the sensors. So that's flat mesh, and you can see from the little schematic over here that you've got a whole series of nodes that talk to each other and relay data in a series of hops back to the big green dot, which is our gateway, which will then transmit the data via the cellular network, generally using the cellular network at least, to the cloud. If, on the other hand, you need longer range, if you're looking at a citywide application or a large opencast mine site, for example, or you want to incorporate more nodes, up to 1,000, then the logical choice is a LoRaWAN system, which sits at a much lower part of the radio, lower frequency part of the spectrum. Our LoRaWAN system is called GeoWAN. It enables long-range monitoring, and it has those advantages of bringing in more nodes over a longer distance. It does come with the expense of lower reporting rates. You can only use single sensor types, and you do need mains power to run your gateway. So there are some constraints there. And we just looked at a mesh-based system where the nodes talk to each other in a series of hops. This is different. The nodes here all communicate on a point-to-point basis. They transmit with a unique path back to the gateway. So you don't have the level of robustness and self-healing that is built into a mesh system. And that data, well, you need to get your hands on it, you need to get your eyes on it. In the first instance, with the systems that we use, the data will be collated and viewed in a web-based portal called Web Monitor. And from there, you've got options to use an API or one of the conventional, I suppose, proprietary visualization platforms to get more out of that data. So let's look at some applications. And I think construction is a good place to start. If we consider some of the challenges on a construction site, then typically we've got time pressure. We may need to repeatedly move the monitoring as the construction progresses. We may have busy, congested site conditions with a risk of machinery damaging the kit. We may well have concerns around the risk of harm to people, surveyors or engineers. And if we can find a way of gathering data from awkward places like confined spaces or height by putting instruments rather than people in those places, then that's generally seen as a good thing. So if we take a typical construction site, that may comprise excavations, it may comprise tunneling or big pipe work, it may comprise tall building construction, retained elements of, in this case, a previous facade of a building, and neighbours with important property that are in close proximity to our construction site. And I think that there are ways in which the suite of wireless technology can help protect and assess all of those elements of the site. So if we start here underground, we've got our millivolt integrator sensor, which can allow us to incorporate a number of borehole related instruments. So we can bring a piezo into the system to look at poor water pressure next to the excavation. Connect to an extensometer for displacement or an inclinometer for deformation. The tilt node, where we just looked at these are pretty much our most used, most favorite tools, measuring rotational movement, hundreds of applications on a site. And in this case, well, we've just picked a couple of them. So a temporary structure here, looking at the crane base here so that we can be installed in just a few minutes. A nice discrete little object, no trailing wires. It can be hidden somewhere in a corner where it'll be protected. It looks quite huge here. It's really not much bigger than a tennis ball, and it'll give us early warning of any sort of incremental or, I suppose, heaven forbid, sudden movement of the crane base. And the other example that I've pulled out here really is looking at the adjacent property. In this case, a rather nice kind of historic stone building, and obviously we want to look at any movements that our excavation activity are causing to the neighbours. We can take one of those tilt beams in isolation, tilt sensors in isolation, and look at what's happening at that specific point, or we can mount it to what we call a tilt beam. So this is a lightweight, rigid stainless steel beam with joints that allow for thermal expansion and contraction. And this enables us to look at movement over a longer area, a wider area. So, for example, here we've looked at the ring beam around the excavation, and we can look for settlement of that. Or we can look at movement within the tunnel in this particular site. And another sort of classic application, I think, is where we're looking at masonry brickwork structures, where we feel that the movement of an individual brick, for example, could be not necessarily representative of the wider structure. A brick tunnel lining, for example, is capable of plastic movement, wider deformation, and if we're interested in that, then we need to use a tilt beam to look at that wider movement. Excuse me. Moving around our construction site in this little quick tour, We might be interested in looking at temperature, for example, curing of concrete in isolation, or we might be using a temperature sensor incorporated with a tilt sensor to look at cyclic patterns of movement. For example, here on the steel structure, we can look at how that behaves differently through the day as the sun hits it, and then it expands and then cools later in the day. Other applications in rail, looking at critical rail temperature alerting, or in heating and ventilation systems, the temperature that monitoring system can be quite useful. In terms of temporary works, in this case, prop loads within the excavation, we could use a vibrating wire strain gauge, and we find that the loads within these props can vary, I think, quite significantly with temperature and other factors. And by spot welding or gluing the strain gauge to the steel tubing here, we can get a data that will allow us to look at the axial loads, the bending moments in the tubular steel props. And the benefit of that is obviously we reduce the risk of failure, but also we can often enable the number of props to be reduced, to be optimized, giving us less cost, reduced cost, and more headroom to operate machinery in that excavation. And then moving a little bit further along the same prop, we can look at the joint, the crucial work done by the load pins. We can measure the load, the strain within those pins with a wired sensor. So another example of the same sort of technology. Looking at the retained facade, a crack sensor applied here to look at the relative movement across that crack. Obviously, getting to that point and manually monitoring the movement of an old-fashioned telltale would be difficult. Here, once this is installed, it's fairly painless. And there's a range of other applications as well as cracking. It could be used for the relative movement across a pile separation, or a bridge joint, or other sort of common applications. Just to look at an example before we move away from construction, fairly typical construction site. This one is located in leafy Harpenden in Hertfordshire. It's construction of a 5-story apartment block with excavation for a basement, but it's not unusually, it's very close to existing residential properties, and a piece of wall which is actually a listed structure, and a pretty straightforward, relatively routine application of this sort of technology using 22 tilt nodes, a single gateway, employed at an early stage in the construction in order to get baseline data throughout the construction and for a short period thereafter. So fairly common application of this sort of technology in a construction site. That could be there in this sort of site as application for a year or two, often less. And the same equipment could be redeployed to other sites and reused in other places. You can see here the tilt nodes mounted to the masonry on short 1-meter tilt beams. So moving swiftly on, away from construction, to the world of railways, and a variety of applications here, particularly looking at track and at earthworks. Well, we've got a familiar set of our family of sensors. I'm not going to dwell on them now. I think we're probably fairly familiar with them now. And they're applied to the structures, to the track in that railway environment. But they're also something we haven't seen in the examples so far, applied to the earthworks, to the slope above or below the railway. Now, slopes are a hot topic at the moment. Climate change is putting increased pressure on the stability, the integrity of earthworks on the UK rail network. The number of slope failures is increasing with hot, dry summers and extreme periods of prolonged rainfall in the autumn and winter. So Network Rail have worked with this sort of technology over a period of quite a few years now. And I really wanted to show the result of that. So the challenges that I think are faced here are numerous. For a start, the assets are old, mostly over 130 years old. They predate geotechnical standards. They're mostly extremely steep compared to modern earthwork constructions. They're often at awkward places to get to because they're a long way away, or they're in the middle of a suburban, densely populated residential area. They're difficult to get to. There's a lot of them. There's 191,000 cuttings and embankments on the UK rail network, plus London Underground and others. And they're vulnerable to climate change. So I think going back before my time in Senceive at least, but quite a few years ago now, a number of measures were taken to explore the use of tilt sensors as a way of looking at both incremental long-term movement of slopes as well as sudden movement, detection of sudden movement events. So many of the existing sort of technologies that are out there are reliant on scheduled sampling in order to preserve battery life. Now, if you're running trains down a track every, if there's 10 trains an hour, 20 trains an hour down a busy suburban track, it's no good just getting data updates every 30 minutes. You need something that responds to events as they happen, or very, very close to that. So the responsiveness that's built into the high frequency flat mesh platform enables us to have a system that is smart enough to wake up if there is sudden movement and take readings outside its scheduled pattern of readings. So if one of these tilt sensors in what we call our InfraGuard platform detects movement of more than 1 degree per second, it will wake up and send an alert, regardless of that sampling schedule. If I could just show you a little animation, I think that becomes a little bit more clear. So in a passive stage 1 environment, all the sensor nodes are reporting on their preset frequency using very little battery, and no movement is detected. Routine updates are sent. A photograph, a couple of photographs a day will typically be sent through an online database. If one of those nodes picks up a small degree of movement, then it will request a photo from the nearest camera. It will send a low-grade alert to the stakeholders, and the other nodes will continue to function as they were in their low-power mode. So if things get a little bit more Hollywood, and we've got a larger scale movement that's detected by numerous sensors, then all of the nodes in that area will be set to transmit at their highest frequency. A high level black alert will be sent to the stakeholders, and a picture will be sent as soon as the network can support that. So this is a really neat integrated system that comprises the sensors that detect the movement, the camera that can give you the picture of what's happening, and the gateway that can communicate that, typically within a couple of minutes to your mobile phone or your desktop. And typically these things, of course, happen at around about 2 in the morning on a Saturday night, because that's the way it is. So those alerts will come through to you in time to either send out people to deal with it on site, or to slow down or stop the trains on that track if the pictures and the data suggest that's necessary. I think it's worth looking at the imagery from those cameras. These are bespoke cameras that are built specifically for this application, with software that is able to deal with low light conditions. We obviously can't use a flash or illumination based system where that could disturb train drivers. So this is a system that relies on the software to intensify what is the available light. And we can see here a picture that's taken around about midday on the left and around about midnight from the same site on the right. So it's a functional system that is good enough to be able to see whether there's been an incursion of material onto that track. It's also a good enough system to pick up in the event of a deer coming along and rubbing its backside on one of the tilt nodes or something else like that happening. raising a false alert. So it gives us eyes on the site. And if I just look at an example here, this is a particularly troublesome and challenging site at Wadhurst in Kent. Readers of ground engineering and other publications will be, I think, familiar with it. I quite like this example because it demonstrates the system working in both modes. In this piece of data that I've got here, you can see data taken over a 12-hour period and a significant noticeable spike, a movement of over 200 millimeters, which took place accordingly at about 2:40 in the morning. And I bet that was on a Saturday. So we've got that detection of sudden movement from a single tilt node. And if we look a little bit further back in that time scale, you can see over a 5-day period that there were a series of very small and incremental steps, which in hindsight could be taken as being indicative of that movement leading up to the sudden collapse. So I think that's an important area, and I think that as time goes by and we look at more data from these applications, the ability to not just detect but also predict slope failures is going to become quite interesting. So if you wonder what a couple of 100 tons of soil and earth and sand descending towards the magnetic attraction or the gravitational attraction of the Earth's core, then that's what it looks like. You can see this major slippage on the steep slope above the tunnel portal. Material did get down to the track, obviously causing disruption, delay to traffic on that part of the route. So that's what it looks like. A network rail are faced with hundreds of these to varying degrees per year, many of them relatively small, but still able to have the capacity, I think, to cause a lot of disruption and even danger of derailment and risk to life. So this system is now installed on over 40 kilometers of track. There are over 20,000 sensors with cameras and gateways installed, mostly in sites in southern England. So if we move on to the final part that I'm going to cover really now is looking at track applications. We can use a variety of different, I suppose, geodetic survey options to gather data about track movement, particularly in the form that permanent way engineers are interested, including cant, twist, a longitudinal settlement, or change in profile, or lateral movement, or slew, or track buckling. So I'm just going to pull out a couple of those really. If we start with slew, this of course, hot news in the hot temperatures last August when a lot of the network was closed down because of the risk of steel rail buckling in the heat. Well, one way of getting early warning or practical understanding of that is to use the optical displacement sensor mounted to a physical object, looking at the rail, detecting localized lateral movement of that rail in the form of buckling, and presenting that together with a graph showing movement and temperature, in this case over a 5-day period, where the red represents temperature and the blue represents movement. In practice, well, this is quite widely used. You can see here installation at a tunnel entrance in the West Midlands using the optical displacement sensor on the masonry wall. And the other example I wanted to pull out was how we can measure change in track twist movement using the tilt node fixed to a sleeper. And at this particular site, we've got a cause of movement, adjacent construction activity. We've got nodes on every third sleeper, and where there is a differential movement of one rail, in this case, the rail nearest the excavation is settling, and a couple of those nodes picking that up in our web monitor platform. So just really a snapshot there of how that can be used. And there are thousands, probably tens of thousands of nodes out there right now in use on the network, looking at those types of condition. an example relatively close to my home in Cambridge at least, and this is the A14 viaduct construction, where tilt nodes were installed on the East Coast Main Line before, during and after the construction of that major viaduct. So on that note, I promised to take 30 minutes, Pete. I've gone over by 25 seconds by my count, so I'm not going to tell myself off too much, but I will hand over to you.
Thank you, Simon. Great job. In fact, you've done such a good job, I'm thinking of letting you carry on. Yeah, thanks to Simon, my colleague. I'm Peter Jones. I've been with Senceive about 4.5 years now. But like Simon, I'm an old timer. I've been in the business, whether it's foundation engineering, PAL testing, for about 35 years, since 1988. And of those, I've worked about 23 years overseas. So together we have quite a lot of experience in this sort of business. So in terms of infrastructure, obviously, Simon has gone through rail and construction. There's a lot of compatibilities, a lot of the same sort of issues and metrics and monitoring that we tend to monitor, whether it's for construction or it's for infrastructure. So it could be roads, it could be tunnels, it could be dams, and the similar sort of instruments such as piezometers, tilt nodes, crack movements are very similar in the infrastructure world as well as rail and construction. So I won't go through all the particular types of instruments again, which Simon has already gone through. So we'll just look at a few examples of where we've used them. So obviously with assets, there's a lot of aging assets in the UK and a lot of countries. Obviously, their assets are much newer than ours, which doesn't necessarily mean that you shouldn't monitor them. I'm a big fan of monitoring from new, so we understand what the normal movement, the normal performance is of an asset. But if I was an asset owner, I'd want to increase the lifespan of my asset. I'd like to increase the utilization. And if we can monitor them, then obviously we have a better understanding of how long we can increase the asset use from a safety point of view. So obviously there's many issues of bridges and structures failing. So structural health monitoring is absolutely of imperative need when you're talking about the older infrastructure. As I said, to a certain extent, a smaller amount of monitoring is good on any structure, but the older it gets, the more things start going wrong. So we need to do a little bit more of the monitoring. And obviously there's a lot of pressure to sort of take people away from sites in rail to keep boots off the ballast, as they say. So, and I think also COVID has to a certain extent shown us that when things happen, such as we're prevented from moving around, it's good to have that instrumentation there, monitoring remotely, always giving you that information. Can you just, next slide, Simon? So this is the first example. It's one of the earliest big projects we did, which is Bromford Viaduct in Birmingham, part of HS2. The blue lines are basically showing the direction of the HS2 tunnels underneath the Bromford Viaduct and also a bit of the Network Rail tracks. So essentially, it's a construction activity monitoring plus an asset monitoring activity. All in all, I think we had probably 3,000 sensors being monitored. We were obviously not doing the monitoring, it was Murphy Geospatial, but our wireless system, the flat mesh system, was able to bring in those 3,000 sensors into essentially one platform and one project. Of those sensors, there was maybe around about 2,000 strain gauges, and at that time, when we are able to innovate, we produced a 12-channel vibrating wire node, which allowed the monitoring contractor to bring all those sensors together without a huge number of nodes. But altogether, I think we had probably 800 nodes which were reporting into Web Monitor for strain gauges, for tilt, for crack sensors, and a few other metrics as well. So quite a big project. It showed that monitoring on a wireless platform can be scaled up to quite big amounts. Next slide, Simon. This one is an example of tunnel monitoring for the potash or the polyhalite mine in York with Strabag. We've been supplying our GeoWAN system for this project, and not every ring, not so many rings are monitored. Usually about once every 100 meters, Strabag will do a monitoring ring to check for deformation after the tunnel segments have been laid and the TBM has moved forward. So obviously they're looking at the short-term monitoring effects, the deformation that can happen after construction, but also from a long-term point of view, they want to see if the tunnel is going to deform over time. Next slide, Simon. Now, obviously, a tilt sensor by itself is not going to give you tunnel deformation. So you have to use a number of tilt sensors to be able to build up a wire diagram picture of how your tilt sensors are going to change, or how the tunnel deformation is going to change as the tilt sensors change. Can you bring on the next slides, Simon? So with a precast tunnel section lining, it's quite easy because each of the segments acts as a single beam. So you need to put a tilt sensor on each of the segments. You create essentially a wire diagram baseline of all the existing tilts at the start of the monitoring period. It needs a bit of trigonometry, but obviously as the effective beams, which are the segments, change direction, maybe move slightly in either direction, the tilt will change, and you can create a new wire diagram, which gives you that ability then to to calculate how the nodal positions have changed through that change of tilt. Next slide. Another project that I was involved with for AECOM, essentially Chipping Sodbury Tunnel. They were lowering the track by a couple of 100 millimeters to be able to put in the OLE cabling at the top of the tunnel. So as they basically removed the track on one side, they monitored the existing track, which was still running at the time, so that during the actual construction, during the lowering of the track, the full length of the tunnel, probably around about 1.5 kilometers, maybe more, maybe 2 kilometers, was monitored during that construction process. Once the new tracks had been put in position, the nodes were then put onto the new track sleepers, so that the ballast and foundations of that new track could be monitored for, it was I think about 2 or 3 months, to make sure there was not going to be any settling in problems occurring. Additionally, the tunnel itself was expected to deform due to the reduction of the track base. So there was a number of tilt beams which were installed by AECOM. Unlike the tunnel, the potash tunnel, which I just showed you, AECOM were able to analyze the deformation by a series of non-interlocked beams. Now, there's something that obviously we don't do. We just provided the equipment on this case. But I think if you're going to be looking at analyzing deformation with non-interlock beams, you obviously need a much greater skill. So our skill was supplying the equipment, and AECOM's skill was actually interpreting the data and checking that there was no deformation in the tunnels at the same time. Right, Asticus building, this was quite an interesting project where a lot of times maybe the surveying aspect, the geodetic aspect of monitoring is not really compatible with the surveying, but I think in this case, then there was definitely a surveying aspect as well. So essentially the top floor of this building was cut off. There were 4 main columns in the building itself. The 4 columns were cut, and the building was actually jacked up by around about 4 or 5 meters so that they can actually install or create another floor in the building. So what we had was essentially 4 optical displacement sensors, which were monitoring the movement of the jacked up floors, probably at every 30 seconds, so that there was no differential tilt problems occurring as they jacked up the building. In addition to checking for the differential settlement problems that could have occurred, because they've got all these they've got these separate jacking systems at each column. It was obviously then a cumulative check of how high the top section of the building had been jacked, because it was being jacked in increments, and then they would repack the jacks and then jack again. So it was a combination of checking how much the building has been, the top floor has been jacked up, but also checking for differential effects that could have been very problematic as the building was still in use.
2 minutes, Pete.
Yeah. Next slide. Chester walls, an example again of use of tilt sensors in a different application as to obviously all the ones we've used before. The walls of Chester are Roman origin, 2,000 years old. There's been quite a few collapses. So while they're actually waiting to do the repairs, we've been providing tilt sensors to monitor the walls to just check that they're remaining stable or where they are continuing to move. Obviously, the client and Chester County Council are aware of where they should put their resources first in terms of doing the construction to repair all these collapses. Next slide. Use of tilt beams and tilt sensors again to give a differential settlement profile. We all know tilt sensors by themselves cannot measure settlement, but when you connect them through a chain of interconnected beams, you're able to produce a deflection profile with some limitations. The 2 ends of the profile are considered to be not moving, and that's where surveying would need to be brought in to obviously have a real survey of the actual movement at the ends of the beams. But what the consultant who took the data was able to do was to create a heat diagram, whereas if you can see at the very start where it's all red, that is essentially where the starting point of the beams. Obviously, we put the beams in after the settlement, the scour settlement that occurred. Then over time, you see where the blue has developed, that is the increase in settlement that was occurring in that bridge over the period of a year before they were able to do the remedial works. So it was quite an extended amount of extra settlement recorded over the period, which was just continuing to happen until they did that remedial works.
Thank you there, Pete.
Is that the last one, Simon?
I think so. So,
okay.
Thank you for that. I just wanted to wrap up with a single little summary slide, really, where I think that I'd hope that we've given you an overview of this sort of technology, that we can answer quite a lot of questions, but not everything. And I think that I'd hope again that we've highlighted the benefits of this sort of technology, and that it can be installed very quickly without specialist skills, that you can get lots of data from high frequency sampling, far more than you could get from a conventional approach, that it's a sustainable approach, it can reduce your travel and carbon footprint, that it delivers benefits over a very short term up to a very long term, and hopefully over those sort of combination of advantages, that it can save you a bit of money, provide a cost-effective solution that can reduce risk and give you a useful tool in the toolkit. So that's pretty much us done for this session. We'd be pleased to hang on and answer any questions that you might have. Unless I'm looking in the wrong place on here, I'm not sure that I'm seeing any questions in the chat. It could be that we've done such a great job, Peter, that there's nothing else to know, or that everybody's asleep, or I'm looking in the wrong place.
It's just the one asking for the presentation, yeah? Well, it just means we can have an early lunch, Simon.
Yeah, yeah.
You've just got a couple of compliments, guys, which you deserve, so there's no other questions at the moment.
Okay, Heather, I am looking in the wrong place because I can't see them. Oh yeah, very useful, thanks. It's James.
Can I just say that any questions can be sent to us just normally, and we'll answer them. Oh, there's a few coming through. Cost of the sensors, we wouldn't give you that over the presentation, but we're more than willing to send you a quotation if you can send us the details of what sensors you'd look to purchase. The type of solution also helps as well, what you're looking for. We don't generally just give out unit prices. So if you can give us a bit of a background of the job, we can give you a project solution. How we forecast the sinkhole during tunneling? Well, I don't think our sensors would be able to do that, quite frankly. Thank you very much. Please, could you make the present available? Yes. Are tilt sensors effective for boring under rail if there is potential land slippage? I think maybe you mean by that when boring under rail, you're talking about pipe jacking or excavating under rail. Obviously, anything that is going to move, is going to rotate, we can use tilt sensors to, in some form, whether they're on a stick, whether they're on the track. Not exactly sure what the purpose would be for that one, but definitely send me an email and we'll be able to give you a little bit more of a precise answer in terms of what you're looking for. Do we provide turnkey solutions or just provisions of hardware? We actually provide what I would say turnkey or equipment solutions as well as to people who just want to buy the hardware and they know exactly what to buy, we can just give you a price. For a lot of companies, they're not really sure of how they should approach it, so we can actually propose to them a solution with our equipment, which I suppose is a turnkey solution. Are you able to use non-GSM radio networks? Oh, that one just disappeared. Bolt pressure, for example, on a wind tower. I think ultimately with a lot of the sensors available, if you can get a sensor that can measure some sort of pressure on a bolt and we can connect it into one of our interface nodes, then yes, everything can be, all data can be collected. It's just a matter of, we're not a sensor manufacturer. Apart from our niche tilt sensors and ODSs, we obviously provide the node interfaces to be able to connect up to external sensors and bring them into a wireless network. So if you can find the sensor that can measure the metric you're looking to measure and can connect into one of our nodes, whether it's an MV5 millivolts, so it's a vibrating wire node, yes, definitely we can. InfraGard.
Question there about InfraGard, the insertion of the stakes. That's typically, the work that's been done with Network Rail is, a lot of it has been around making the system repetitive and able to be rolled out on a very large scale. And the optimal way of inserting those stakes has been found to place them as close to vertically as we can. It's not critical that they aren't absolutely vertical, but to a standard depth of 0.5 meter. So they're typically driven 500 millimeters into the soil.
Yeah, just touching on that, obviously we've developed that with Network Rail. Network Rail have their own particular requirements that they want. There is no definitive embedment depth. It really depends on the type of soil conditions. Maybe if you've got a very rocky soil, you wouldn't go in 0.5 meter. So it's really a matter of just having a stake which is stable in the ground, is not able to move. As Simon said, it doesn't have to be straight. Obviously it helps if it's straight when it goes in, but it can be, you don't need to take the spirit level with you when you putting in these stakes. The GSM radio networks for monitoring in remote locations. Yeah, unfortunately, I think at the moment we do just have GSM, unless there is an internet connection in the middle of the jungle or in a very remote place. We are looking at incorporating satellite technology into our gateways. It's something we don't have at the moment, but obviously in future, then there will be, I suppose, a non-GSM radio network as well for gateway backhaul. Can you also use a system when you don't have mobile coverage with a Wi-Fi hub?
Yeah,
if you have Wi-Fi internet, definitely you cannot use our cellular gateway. We will produce a bespoke monitoring hub where you can actually put in the necessary Wi-Fi modules or internet modules that you need in that particular area. But yes, as long as you've got an internet connection, whether it's Wi-Fi or direct, or there's a cellular signal, then there's no problem getting the data backhaul back to the web monitor.
Okay, there. I think we're beginning to come to the end of the questioning here, Pete.
Yes, it looks like. So, as I said, any questions can be directed to myself or Simon just through our normal emails. Maybe Simon can add them to the text, to the questions and answers. So you can contact us directly if you have any particular technical question which you want answered, or you want a quote for a particular project or solution.
The email address that's on the screen there, the info@Senceive, is a catch-all, but I guess really the other simple one is your email is pjones@senceive.com, which is another pretty good place to send an inquiry. But yeah, I'll make the PDF, make the slides available as a PDF, and I'll make sure that contact details are available in there. So that's another good reason to get hold of those. So I think on that note, we're going to say thank you very much for attending today, wherever you may be. Hopefully it's been useful and informative, and yeah, delighted to have so many people on the call today. Thanks very much from me.
Yeah, thank you.